Our next speaker is Koichi Oyakawa, who will be speaking a little bit about small cancellation groups being bi-exact.
Thank you for having me. Today, I will talk about my recent work on bi-exactness and small cancellation groups. And first of all, bi-exactness is an analytic property of a group. So very roughly speaking, what I did is showing an analytic property of groups from its geometric nature. So let me start with explaining what is bi-exactness. But before doing it, we need some preliminaries. So first of all, amenable action of a group is needed for explaining exact groups. So a group G, let group G acts on a compact Hausdorff space, then the action is called topologically amenable if for any real number and a finite subset of a group, there exists a continuous map from the compact space to the probability space of the group. And this probability space of the group is identified as a subset of L1 of G, which is a Banach space. So these measures have L1 norms. And with that L1 norm, we can say the map is an almost G equivariant, meaning the inequality. And by the way, this continuity is a little tricky. It's not continuous with respect to the L1 norm, but because the probability space is a subset of L1 norm and, L1 space, and the L1 space can be considered as a dual of C0 of G, which is a space of functions that vanish at infinity. So this L1 space has weak star topology, and the continuity means with respect to the weak star topology. So now an example of a topologically amenable action is any action of an amenable group on compact Hausdorff space. So I will explain the proof. And the proof is not difficult by using Fornor condition of an amenable group. And this is the only proof I explained today. So given a positive real number and a finite subset of G, by Fornor condition, we can find a finite subset that is almost G invariant. I should say F invariant. So the symmetric difference is very small with respect to the original size of the set E. Then using this set is called Fornor set. So we can define a map from the compact space to the probability space as a constant map. So for any point of the compact space, we assign an probability measure that is an average of the characteristic map of the Fornor set. Then for any element of the finite set and any element of the compact space, when we directly calculate the L1 norm of the difference, then because this M is a constant map, M of X and M of GX are both the same element. And G times the characteristic function of E is exactly the characteristic function of G times E. And this difference of L1 norm, or the L1 norm of this difference is exactly the symmetric difference of the Fornor set, which is less than epsilon. So this M constant map gives a map for the definition of the topologically amenable action. So now a group is called exact if it admits topologically amenable action on some compact Hausdorff space. And by the proof of this example, it's straightforward to see that a group is amenable if and only if its action on one point is topologically amenable. So we can consider exactness as a kind of generalization of amenability. So now we can define bi-exactness. So a group is called bi-exact if it is exact. And in addition, there exists a map from the group to the probability space of G, satisfying the following a little weird conditions. So for any two element of G, when we consider the following a weird difference and take L1 norm, then this goes to 0 as x goes to infinity. And by the way, this x goes to infinity means that this x escapes any given finite set of G. So in other words, it goes to infinity in one point compactification of the group G. So bi-exactness, it's a property that is in between amenability and exactness. So it's weaker than amenability, but it's stronger than exactness. So why this property is important? That is related to the field called operator algebras. So in 2004, Ozawa proves that any group phenomenon algebra of non-amenable bi-exact ICC group is prime. And here ICC means infinite conjugacy class, meaning that for any non-identity element, its conjugacy is infinite. And I don't know how many people are familiar with phenomenon algebras, but it's just a very nice algebra that is constructed from the left regular representation of G. And it's a subalgebra of the algebra of bounded linear operators of L2 of G, which is an Hilbert space. And here primeness means it cannot be decomposed as a tensor product of two 2-1 factors. And here, again, a 2-1 factor is a very nice phenomenon algebras. And also I should mention that originally, as far as I see Ozawa's website, he wanted to, before this theorem, there was a famous result that group phenomenon algebra of a free group, a non-amenable, or a free group of rank 2 is prime. And his motivation of proving this theorem was generalizing that result to any hyperbolic groups. And in proving that hyperbolic group phenomenon algebras of hyperbolic groups are prime, he found this property of bi-exactness. That is the original motivation he defined bi-exactness. But it turns out this property is very nice. And this is another theorem by Ozawa and Popper, and it's called unique prime factorization theorem. So when we are given a finite non-amenable bi-exact ICC groups, and suppose the tensor product of these phenomena algebras are decomposed in another way as a tensor product of prime 2-1 factors, then first of all, these components, the number of these components must coincide. And moreover, after permutation of indices and unitary conjugation of these phenomenon algebras, each of the factors coincide with the original group phenomena algebras and after amplification too. But I won't explain what is amplification or what is unitary conjugation, though it's not very difficult. So what these two theorems says is that the group phenomena algebras of bi-exact groups or non-amenable bi-exact groups can be considered as a kind of prime numbers in number theory, or something similar to prime numbers in number theory. And there are many other results about bi-exactness. So people in operator algebras, what I want to emphasize here is people in operator algebras are very interested in this property. So now, as a group theorist, a natural question is, what is an example of a group with such nice property? So first of all amenable groups are bi-exact. And this is kind of trivial modulo some equivalent conditions or some equivalent definitions of bi-exactness. So one equivalent definition of bi-exactness is that it admits topologically amenable action on a very nice compact space. And because we showed that any action of amenable group on compact space is topologically amenable, by using that definition, we can see amenable groups are bi-exact. Now, secondly, any discrete subgroups of connected simple Lie groups of Lancron. To be honest, I'm not very familiar with Lie groups, so I cannot explain it much. And thirdly, any hyperbolic groups are bi-exact too. And we can show this by considering its action on Gromov boundary. And finally, the two semi-direct product of SL to Z. This example was proved by Ozawa himself. And here, what I have to say is, so as I said, amenable groups are trivial, and discrete subgroups of connected simple Lie groups and hyperbolic groups are two examples Ozawa listed as an example of bi-exact groups when he defined this property. So what is surprising is after he defined bi-exactness, only Z2 semi-direct product of SO to Z is found. So I would say bi-exactness is not understood very well from group theoretic point of view. And by the way, there is some result on permanence property of bi-exact groups. For example, any subgroup of bi-exact groups is bi-exact, and free product of bi-exact group is bi-exact too. And for example, a relatively finitely generated relatively hyperbolic group is bi-exact if and only if all peripheral subgroups are bi-exact. That is my result. But I should say not many known about a class of bi-exact groups. I mean, which class of groups are bi-exact? Okay. And my result is, for my work this time, I'll push this direction forward. So any finitely generated C prime 1/33 group is bi-exact. And one thing that is important here is I don't assume a group is finitely presented. So I think many of the audience here are familiar with small cancellation groups, but I want to review what is small cancellation groups to explain what my result is. Okay, so small cancellation groups are groups defined by group presentation. So we put special condition on relations, and that condition is given as follows. So first, let x be a letters, and f of x is a free group generated by x. Then, given two words, reduced words that are distinct, we can define what is called a piece. So a piece is essentially the common intersection or common prefix of these two words. For example, when letters are 3, so f of x is f3, and when we are given two letters, u and v, as follows, then because first letter and the second letter, b, are common between u and v, but the third letter is c in u and c inverse in v, so these two are different letters. That's why a piece of these two letters is AB. And small cancellation condition, it's saying the given two words in a relation, the piece is very small compared to the length of the relations. So if for any two distinct relations, the length of piece is less than the lambda times the length of the relations. Okay. And for any real number, if a group has a presentation that is a C prime lambda condition, then the group is called C prime lambda group. And here, the relation being symmetric means that all letter or all words are cyclically reduced. And if one word is in the relation R, then any cyclic permutation of R and R inverse are also in the relation. And if in addition the letters are finite, a letter is finite, then by definition we call the group is finitely generated C prime lambda group. Okay, so one natural and very famous example is a fundamental group of a surface. And that is given by the product of commutators. And this satisfies C prime 1/7 condition. And by the way, any finitely presented C prime 1/6 group is known to be hyperbolic. So you might think my result is not very different from the fact that hyperbolic groups are bi-exact, but it's not quite true. And that you can tell from the next example. So because my group doesn't need to be finally presented, when we take an infinite presentation, for example, this satisfies a C prime 1/6 condition. And then this group is not even relatively hyperbolic. So the class of finitely generated C prime lambda group is very different from the class of hyperbolic groups. Okay, so that's one important point of my work. And another important point is related to a property called a proper proximality, which is another analytic property of a group. So actually, the definition is not I'm not very familiar with the definition either, but I will explain just for the clarity. So let G be a group, and it acts on a compact space again, and take an auto filter of G. So it's an element of the Stonechek compactification of G. Then we can define some property on the element of the Stonechek compactification as follows. And okay, so whatever this property is, a group is called properly proximal if it admits a nice action on compact space again. So there exists a finitely many action on compact space, and each compact space has a probability measure, and this probability measure and the action satisfies the following two conditions. First, this action doesn't admit invariant measures. Secondly, auto filter of the group has nice property. Okay, so whatever these conditions are. So my work is related to a work of Forbes, Fang, and Lukuyu. Okay. So by the way, this property of proper proximality is considered as a kind of generalization of bi-exactness. And this was defined by three operator algebraists, Raymond Boudonnet, Adrian Ioana, and Jesse Peterson. And they show very nice property of group von Neumann algebras of group having this property. And these three people studied proper proximality from group theoretic point of view. And what they did is various groups acting on cat0 space are properly proximal. And after proving those results, they asked whether the following groups are properly proximal or not. So the first one is group acting properly on proper coarse median spaces. Secondly, group acting on spaces with convex geodesic biconvex. So these are a kind of generalization of groups acting on cat0 spaces. And thirdly, systolic groups and automatic or biautomatic groups. And finally, small cancellation groups. So they write it in their paper. And the corollary of my previous theorem is that any non-virtually cyclic finitely generated C prime 1 over 33 group is properly proximal. And if a group is amenable, then because the compact space has invariant measures, amenable group is not properly proximal. So the case in this corollary, the case of virtually cyclic group is obviously non-properly proximal. So this corollary sufficiently answers the final question on small cancellation groups. Okay. And all other 4 groups are still open. Okay. That's the end of the talk. I forgot to insert thank you, but thank you for listening.
All right, thank you, Koichi. All right, does anybody have any questions? You can unmute yourself. Well, I think you know what my question is going to be. How about graded small cancellation? Do we know anything about that?
Oh, sorry. What group?
Graded small cancellation. So, for example, free Burnside groups.
I think, first of all, not all graded small cancellation groups are bi-exact because some graded small cancellation groups contain Gromov monsters. That is not exact. But I think there is some hope to generalize my result on proper proximality. So it might be possible that graded small cancellation groups are properly proximal, but Yeah, I think it's an interesting question.
There's no other questions. Let's thank Koichi again.